your first order ODE is of the form dy dt equals f of ty, meaning if phi of t is a solution, well, okay, let me not say if. Phi of t is a solution if and only if. It's an if and only if. When you plug it in the left-hand side and the right-hand side, you get equality for all t in some small interval near your initial condition. Phi prime of t equals f of t comma phi of t for all t in some interval. Typically, you want to think of it as an open interval containing the initial value of t. I'll call it t naught, but I'll also call it a. That's what it means for a function phi of t to be a solution. So if we know information about f, like if it's Lipschitz, for example, it doesn't get too big in some strip, too fast at least, that will tell us perhaps some information about the derivative of solutions. Or if perhaps we know it's bounded in some rectangle, we know information about f of ty in that rectangle, like it's bounded, that'll tell us the derivative is bounded. But what about the second derivative? If we're going to use a higher order method, we're going to need to think about the second derivative of solutions, not just the first derivative. You can use the differential equation to figure out what you might call a corresponding second order ODE found by differentiating both sides with respect to t. And if you're using the differential equation notation with the Leibniz notation, what would that mean you'd write? It'd mean you'd write the second derivative of y with respect to t equals, well, what should we do to differentiate the right-hand side? You have to assume y is a function of t. And this is a multivariable calculus function as it stands, a function of two variables. In the context of the differential equation, y depends on t. But if you wanted to think about that function without thinking about y depending on t, you'd say, hey, that's a multivariable calculus function. I'd need to think about partial derivatives. And if y does depend on t, I'd have to use a multivariable calculus chain rule. I don't know if in multivariable calculus, if Dr. Yang shows you diagrams like this. Let's see. Your function here, in this case, f of ty, depends on two variables, t and y. And those variables could depend on some other variable that you could give a different name, like z, if you wanted to, although in our case, it's the same letter here as t, it's t in both spots. And you draw partial derivatives along these lines and ordinary derivatives along these lines, including a funny looking one, dt dt. And you multiply along the paths through the diagram and then you add them. Dr. Yang ever draw diagrams kind of like this? No? Yes? People are shaking their heads no. Okay. It's very funny here because I got the same variable here and here. It's not usually the way you think of this. And I've got a dt dt here. I could more generally call this some other variable name like z or something and have a dt dz here and a dy dz there. But if you conceptualize it this way, what you end up doing with the multivariable calculus chain rule again is you multiply the derivatives along these paths, keeping in mind that everything depends in general on both t and y. So I have df dt of ty times dt dt I guess just of t. It's a little unusual here. Plus the product of the derivatives along the other paths is df dy, which is a function of t and y, times dy dt, which is a function of t. This thing does simplify to 1, as you would expect in this example. Again, if you had some other example that would be more typical, where you have some other variable here like z, you'd have dt dz there, and you might actually have to differentiate it. And it would not necessarily equal 1. But in our context, since both of these variables are the same, a little weird, this does end up being a 1, and this simplifies ultimately to this. Now, again, I'm putting the explicit dependence on t and a y in this notation, but you should realize that quite often we don't bother, and we just write or df dt plus df dy dy dt, where I'm using partial derivative notation with the f because it is a function of two variables. But y being a solution just depends on one variable t, so I use ordinary derivative notation. Anyway, where are we going with this? This is going to give us information about the second derivative of a solution. In fact, I could have even taken this form of the differential equation where I got the solution in there without Leibniz notation and differentiated both sides with respect to it, with respect to t here. If I had done that, though, what I would have gotten is essentially the same thing. If I sort of combine these things, what it means for the second derivative of my solution function is that it has to satisfy a differential equation like this. Everywhere you see, I'm essentially looking at this one here too. Everywhere you see a y, you replace it with phi of t. After differentiation, at least. And this last dy dt becomes a phi prime of t. If we use one more term in the Taylor expansion, we need information about the second derivative of a solution. And this is an equation the second derivative has to satisfy, assuming it's sufficiently nice on some open interval near the initial condition. Yeah, it's kind of complicated. Hang with me. Let's look at how this looks in the book. And then we'll try to apply it to our example. So in the book, it's maybe even a little tougher to understand. Here's the general form of a Taylor method of order n. We are trying to apply this for our example when n is 2. Euler's method applies this when n is 1. Linear approximation corresponds to n is 1. Quadratic approximation corresponds to n is 2. The general setup is very much the same as Euler's method. W0 is alpha, just like before. You could call that y naught. W sub I plus 1 is the old value of W sub I, plus delta W. Delta W still takes the form as h, the step size, times something. With Euler's method, the something there is f of TIW, which gives you the slopes of marks in the slope field. But here now, more generally with this Taylor method, it's written T superscript n of TIWI, where T superscript n of TIWI is this expansion. If n were 1, as it is with Euler's method is a Taylor method of order 1. If n is 1, that h to the 1 minus 1 would be 0, h to the 0, which is 1. This would be a 1 factorial down there, which is 1. And this would be f 1 minus 1, f0. What is that? Is that a 0th derivative of f? Yeah, but a 0th derivative of a function is the function itself. And what that all means is it simplifies to just that. replace the Tn with just that, and you get Euler's method. Now, if I make n equal to 2, the last term, so to speak, has an h to the 2 minus 1 power, first power, over 2 factorial, 2, times, if n is 2, f2 minus 1, I guess that's f1, which is a first derivative. It essentially simplifies to this. This is the t when you apply the Taylor method when n equals 2. But what is f prime? To tell you the truth, I think this is bad notation. I mean, the book is using it because it's simple notation. But if you try doing the reading, you're probably confused by this. Like, what is f prime if f depends on 2 variables? It'd be better to use, I think, DDT notation. I need more paper. I thought I had more paper. Oh, it's under here. It'd be better to use DDT notation instead of f prime of ty in general, or tw. I'm going to write ty. Write ddt of f of ty, emphasizing that y depends on t for one thing. So you are differentiating with respect to t ultimately. Y depends on t. You could write y equals y of t like the book does, or you could use my phi of t notation. And you are differentiating with respect to t. So in essence, you are doing exactly what we did up here when we took this f and did all this stuff. All that stuff is this is the book's shorthand notation for all this stuff. And yes, it's simpler notation, but it's confusing. I mean, yes, this is confusing too. But I think a little less confusing because we're being a little bit more explicit about what's going on. We are using a multivariable calculus chain rule with this diagram and emphasizing that everything does depend on t ultimately. Well, along the way, you do need partial derivatives of f with respect to both t and y. So how does this play out for our example? So again, our example was the SDT equals, I'm forgetting it already, 12 minus 4s over 10 plus 2t. That's my f function of ts. And again, I could have used a y instead of an s. For purposes of differentiating this thing, both with respect to s and t, it might be better to write it as 12 minus 4s times 10 plus 2t to the negative 1 power. So, I mean, that might be easier so we can avoid the quotient rule if that seems convenient. If we're going to use the second order Taylor method, we need to essentially differentiate both sides of this with respect to t, realizing that when we do so, we're assuming s depends on t. We're assuming our function satisfies this when we differentiate it on both sides. And again, that ultimately means doing the partial derivative of f with respect to t times dt, which is 1. And this depends on both t and s, plus the partial derivative of f with respect to the other variable, s in this case, which depends on both t and s, times ds dt, which depends on ultimately t, though actually at the start, it's going to depend on t and s because I'm going to use the differential equation. Use the first order diff eq here is this is really the key step, actually. Use the first order ODE here, meaning this one. To simplify is what I'm trying to say. The partial of the f with respect to t, look at this as a function of t, is going to be, well, the derivative of that is constant, 0. Differentiate this with respect to t, and I am avoiding the quotient rule. I'm looking at this form of it. I'm going to bring the -1 down, get positive 4s 10 plus 2t to the -2, then with the chain rule times 2. That's what that becomes. Plus, what does all this become? Differentiate with respect to s. I get, once again, 0. I'm going to differentiate this with respect to s. Treat the t as a constant. This is linear in s. The derivative with respect to s is everything, including the minus sign, but the s, right? Because, you know, the derivative of 5x is 5. It's linear in s. So I get -4. Don't write the s. 10 plus 2t to the -1. Multiply that times ds dt, where I'm pretending I don't know what the true solution is. Of course we do, but when I'm doing this calculation, I'm pretending I don't know what the true solution is. So I'm using the differential equation. I essentially substitute the differential equation right-hand side for this thing. It equals f of ts. I'm using the first order differential equation. So I write 12 minus 4s 10 plus 2t to the -1. Kind of complicated in this example. The book's example is easier. Is it worth trying to simplify? Probably some, at least. 4s times 2 is 8s, and then I could put that in the bottom, 10 plus 2t squared. And then all this, I don't know, boy. Yeah, I could multiply that through. Is it worth doing? I guess so. Well, it'll be 4 times 12 minus 4 times 12 would be -48. -48 over 10 plus 2t. And then multiply these two, I'll get plus 16s over, I guess, 10 plus 2t to the -2, or 10 plus 2t squared. So once again, if I've not made a mistake, this, and it could be simplified, this is essentially a second order differential equation for my solution. And this entire expression is essentially what the book called f prime of ts. Is there a way I can check this in Mathematica? Let's try. Not there. So, okay, let's remind ourselves what f of ts is. It's right there. What I really want to do is I really want to differentiate that with respect to t. And then I'm going to go ahead in Mathematica write an s of t here. This will differentiate using the multivariable calculus chain rule. And you can see it is giving us something somewhat similar. We've got the 8s over 10 plus 2t squared there. That is the first term we got from df/dt. And this other term that you see, -4s prime over 10 plus 2t, that is essentially this. The s prime comes from this, the -4 over 10 plus 2t is the same as that. So it is using the multivariable calculus chain rule in Mathematica when I do that. But I want to simplify it to what I got here. So what you can do to do that is you can replace S prime of t with the original right-hand side. And here is syntax that will do that. This slash dot, and inside curly braces, S prime of t arrow, F of t, S of t. That's going to take the previous output and replace the S prime with the right-hand side of the differential equation. And that is the same as all this. Notice there is a negative 48 in here, a minus 4 times 12 over 10 plus 2t, and a plus 16s over 10 plus 2t squared if you combine all these things. It's right. This is right. I mean, you could simplify it too. Simplifies to that. That would be the right-hand side of a second-order differential equation that our solution to the original differential equation satisfies. It's going to give us information about the concavity of the solution. It's a second-order equation. What do we do with this? Let's go back to the book now. That entire expression is what we replace the F prime with here in this thing. Though we don't want an S of t in there, we want just a plain S. Just like when we apply Euler's method using nest list, we didn't write an S of t, we just had an S. So maybe I want to use capital T here. And let's see. So this is not going to be the function I actually use in nest list. It's going to be the capital T function here. Capital T of t comma w. And it does depend on h. So I'll put an h in front here as well. In general, it's h over 2 times this f prime, which for our example is essentially all of this. Oh, I forgot f itself here, sorry. F of tw plus this. Essentially all of this, except make it a, you know, an S in general, or if I want to use W, make the S a W. So I'm using these two terms you see on the right here. So I got an F of tw plus h over 2 times this, what the book is calling f prime. But for our example, f prime of tw is this thing, because it corresponds to differentiating the original f of t s with respect to t, assuming s depends on t, using the multivariable calculus chain rule. And we did it both by hand and with Mathematica, and we got this expression. So now we do the Taylor method. Maybe I call it TM2 because it's n equals 2, in the same kind of way we did the regular Euler method. T plus h for the first one, and w plus h times t of tw for the second one. I got to have, I'm using this equation now. The second component here is w plus h times the t I just computed. And this will be the thing we iterate. And I guess I'm using h equals 1. H is 1, I'm going to have to go 45 steps. Just in case, do a slash capital N. Should produce good approximations, hopefully. Once again, yes, close to the 199.8. Right, that was the exact value at t40 equals 45. So the error is 199.8 minus 199.778. 0.022. Is it better than Euler's method? In general, second order Taylor method is better than Euler's method, but in this example, after 45 steps, it's not really much better, if it's better at all. I mean, the error is closer to 0. This error is close to negative 0.1. And this error is like 5 times smaller, close to 0.02 in absolute value. That's why that happened. So it is doing better. And in general, it can be much better. Here they are both doing well. But in general, the second order Taylor method can be much better. And as I was thinking might be the case, this did take up most of our time. Let me encourage you to continue trying to read section 5.2 and 5.3 again. Yes, it's a challenge. I was hoping that we could look a little bit at the theory here, in particular this theorem about Euler's method error. We will for sure look at this next Tuesday. The derivation and proof is not easy, but it is understandable if you work really hard at it. And I encourage you to do so. I also want you to start reading about the Runge-Kutta method, which will start next Monday or next Tuesday as well, and which will be our last topic. And we'll talk about next Thursday as well in more depth. But again, as usual, I'll try to approach things from a way that helps you apply it more easily. Okay? Have a good day.